All right, so statistics is the branch of mathematics where we study how we can learn from data. So this is all about data. So who needs data? In short, everyone does. We all do. Data is around us all the time. It's the central feature of our modern civilization. For instance, in medicine, we constantly need data to test out new drugs, treatments, tests, surgeries, methods, all sorts of things. Doctors, nurses are constantly evaluating data to decide how to deal with all sorts of things. Businesses are constantly gathering data. Every time you click on anything, anytime you watch something on Netflix or buy something on Amazon, they're always trying to use data to say, where can we put a new Starbucks location? What sort of movie should we make next? What sort of product should we make next? Engineers are constantly requiring new data in order to create new designs, testing new equipment, all sorts of things. The government gathers enormous amounts of data, not only through like the census reports, but also politicians, campaigns, polls. Where should we run ads? Where should we have get out the vote operations? As consumers, we are constantly required to evaluate statistics and data. 27% of doctors represent this, 99% of dentists represent this brand of toothpaste. Then we see that all the time. As citizens, we have to decide how to vote for who and why, weighing all sorts of evidence, tax cuts versus budget versus all sorts of things. Statistics are coming at us all the time. And of course, this comes down to the sciences. All sciences are based on data. Data is the fuel of the scientific process in order to test our theories, study new things. Data is the heart and soul of modern civilization. So, all right, we want to think about this a little bit. We want to think about a scientific view of this. The fundamental assumption of all science is that most people are wrong about most things most of the time. Let's face it, we as humans, nobody walks around thinking that I'm wrong about stuff. We all walk around all the time thinking we're right about everything. Human beings are wonderful at being biased, and we pay attention to those people and those data and that information that supports us and agrees with our opinions and perspectives on things, and we're very good at ignoring and turning a blind eye to anything that contradicts us, to saying that we might not be right. So as a result, the whole scientific process has been created as this great big giant error correction process. Scientists double check, cross check each other. Anytime any scientific paper is published, it must go through a series of referees, critics who anonymously criticize and try to poke holes in this. Everything has to be double checked, verified. So, the goal behind all of this is to learn objectively true facts about our universe. So, we should talk about that. Subjective knowledge, human knowledge can be broken down into two different things. There's subjective knowledge, which is a matter of opinion, personal perspective, based on our feelings. And so it's the sort of thing where if two people disagree on that, that doesn't necessarily mean one is wrong. It's just they have two different perspectives on things. For instance, George Washington was the best president of the U.S. There are some people who have that opinion. Other people like Abraham Lincoln. It's not it's not cut and dried, right? Objective knowledge, that's the stuff we want. Facts. Anybody, any person could verify and confirm. It doesn't matter who you are, what your perspective is. We all agree on this. It's based on physical reality as it exists outside of us. For instance, we can all agree that George Washington was the first president of the United States. Whether he was greatest or not, well, that's a matter of opinion and perspective, and different people can have different opinions about that. But objective things are the things that ultimately we all must agree upon. So, how do we get this objective knowledge, this true knowledge that reflects the real world as it actually exists? We must gather data. The data must be gathered in a regular, systematic way that any other person could go out, double check, cross check, verify, make sure it's true. Okay, so this is now we need to think about anecdotal evidence. Our lives are often kind of based on anecdotal evidence. These are the things we remember that stick in our mind based on what we've personally experienced or things we've seen in the media, on TV or stuff like this. For instance, I had a cold. I took one of them pills and the next day I was better. Oh my goodness, the pill cured the common cold. Or, for instance, this. Hey, I met somebody from Canada. They told the funniest stories. And lots of comedians are Canadian too. Canadians are funny people. Okay, so you're right. We can't generalize this. Just based on the stuff we happen to bump into in our daily lives, that's not a reliable way to draw real conclusions about the objective facts about the universe. Real data, useful data, is gathered in a careful, systematic way, following a procedure so that anybody else could follow my procedure, get similar sorts of results. And the other thing is, data needs to be gathered in such a way that if my ideas are wrong, it's going to tell me that. I need to gather the data in such a way that it could break one way or it could break the other. So what does that mean? First of all, data all must be gathered more than once. One case isn't enough to draw any big giant conclusions. I mean, it's because welcome to planet Earth. It's messy here. Anytime we measure anything in the actual real world, it's always going to come out different every time you do it. All right, here's my example. There's this cool old TV show where they did an experiment. They wanted to answer the question, do you get more wet in the rain if you run a certain distance or if you walk a certain distance? You know, one of the questions for the ages, right? So they do this cool experiment. They set up this warehouse with these spraying standard rain from the ceilings, and then the experimenter puts on a pair of coveralls and first walks back and forth through the rain, and then runs back and forth through the rain in a different set of coveralls. And then they weigh the coveralls afterwards, so that see which coveralls were more soaked up. Great experiment, cool stuff. But in the show, they did it once. And so I was like, oh, yeah, well, it's wetter when we ran, so therefore, you'll get wetter if the coveralls were heavier if you run through the rain. But as a statistics guy, I'm like, wait a minute. What about, here's a big idea, the null hypothesis? This is something we're going to revisit again and again and again in this class. The null hypothesis says, what if this thing I'm studying makes no difference whatsoever? What would I see then? So for instance, supposing it doesn't matter whether you walk or you run, you're going to get the same amount of wet either way. What would happen? What would I see? Most people, when I ask this question, say, well, you would see the same thing. The coveralls would weigh the same amount. They would be just as wet one way or the other. And that's wrong. That's wrong because this is planet Earth. Every time you do any experiment, even if you do it exactly the same, as best you can, it will never come out exactly the same. The truth is, if running versus walking in the rain doesn't make any difference at all, the truth is that it would just be basically random. Every time you do an experiment, it's going to be different every time, so it would be a 50-50 sort of chance, whether the coveralls were wet or whether you were walking or whether you were running. So if you do it once, I don't know, does the running make the difference, or was it just a 50-50 sort of chance? So as a result, what we need is replication. We have to do every experiment more than once. We have to test it several times. If I did this with 10 different coveralls walking through the rain, and then 10 different coveralls running through the rain, and all the running ones were heavier than all the walking ones, now we can say something. Now we have statistics. We have data because we replicated it, and it replicated every single time we got the same result. That would be beautiful. And so that's why we always must do everything multiple times with replication. So here's another really, really big idea we're going to come back to again and again. In statistics, our goal will almost always to say something about a population, and that's a very special word. The population means some big, giant, large group of things I want to know about, but I can't actually study all of them. For instance, I want to know what all Montana voters are going to do on election day. I want to say something about all the tomato plants I could potentially grow in my garden. I want to say something about all the boxes of cereal produced by some big factory. Now, I can't gather the whole population. The whole population is a big thing. There's too much out there for me to study. So instead, I gather a sample. The sample is the things I actually gather the actual data from myself. The sample gives us the actual data that I have in my computer. That's my sample. I've got it there in my computer. So that's, well, in this example, let's say I can't talk to all Montana voters, so I gather a few samples. I call a few thousand voters on the phone. I can't study every tomato plant ever, so I grow a dozen of them, and then I see how they work out with one thing or another. I can't measure every single box of cereal produced by the entire factory, so I pull off 50 boxes and I weigh them to see if everything's working well. The sample can potentially tell me something about the population, and that's the awesome miracle of statistics. So here's the idea. I want to learn about this great big giant population out there based on my sample. The sample is something feasible I can actually do. And the wonder of statistics is this crazy thing actually works. I can often accurately predict the results of an entire election based on, with millions of voters in it, based on a sample of only a few thousand. That's awesome. That's wonderful. That's what we're going to learn to do in this class. However, everything we study, these methods, all these techniques, all these wonderful equations will only work if the sample is gathered randomly, by which I mean that every single member of that whole population out there has an equal chance of being in my sample. If every single voter in the state of Montana has an equal chance of participating in my poll, then hey, my poll is probably going to say something very useful. It will be a representative sample. It'll be able to tell me things about all the voters out there. And by randomly, let me be very specific about this. Randomly means I didn't pick them out myself by a person. They're chosen by random numbers from a computer. And so my sample could only represent the population it was randomly drawn from. So this brings up the idea of bias. Now, the bias in this case has a very, very, very specific meaning in statistics. Bias doesn't mean, well, let's see, the beer company did a study of their beer and showed that if you drink it, you become stunningly handsome and popular. Okay, well, that's a bias because the people who are in the study are owned by the people. Yeah, okay. Now, bias in statistics means I have a non-random sampling method. For instance, in 1936, they did this great big telephone survey to predict who was going to be the next president. And they called all people on the phone. But back in 1936, mostly only the rich people had phones. And so they got a huge sample, but not very good results because they weren't talking to everybody. It wasn't a random sample. Or similarly, I could survey the people who visit cars.com to see how many Americans plan to buy a new car. Well, not everybody visits cars.com. Usually the people who visit cars.com are the people who are kind of interested in buying a new car. That's not a random sample of the whole population. If I ask my friends, hey, do you prefer action movies or romantic comedies or something like this? It's like, well, my friends are probably like me, so that's not, no, those are not random samples. And so that's a big problem. Another big problem with people deal with when they do surveys is, for instance, if I hand out surveys, say, everybody visit my website, take my survey, well, most people aren't going to do that. So we have a non-response bias. Only people who care about the issue I'm surveying about are going to respond, and maybe the vast majority of people who really have kind of weak feelings on that aren't going to respond to the survey, and so the survey results don't represent everybody, the whole population, because I've got this non-response bias. The goal is a simple random sample. Everybody in the entire population has an equal chance of being selected for my sample, but that's really hard to do. In lots of cases, it's just straight out impossible. So what do? We do the best we can, and then when we present our study to the world, we explain exactly what we did. Here's how I gathered my sample, and everybody can make up their own minds about exactly how random or non-random it was, and make up their own decisions about whether bias has infected my study and therefore make my results, meaningless. All right, so here's our summary. First of all, science and skepticism. You, ladies and gentlemen, are fallible. You could be wrong. And so therefore we need to test our ideas against the real world by gathering data. Beware of anecdotal evidence, the stuff that sticks in our memories from our life, from the media. Well, yeah, not a good way to draw conclusions because we're really good at ignoring and forgetting the stuff that contradict us. Data is gathered in a systematic way from the real world so that another person could follow our procedures and would get basically the same results, verify and checking our results. We always need replication. We always need to do things multiple times because this is planet Earth. It's messy here. Every time you do an experiment, even if you do it exactly the same way, you're probably going to get slightly different results. And so we got to do it many, many times and study the variation, all that kind of thing. We must reckon with the no hypothesis. What if there was no difference? What would we see? The goal of all this is to say something about a large group of things, a whole population, based on a relatively small sample that we can actually gather the data from. Our goal is that we gather our sample randomly. We have a simple random sample, but often that's hard, and so we often end up with biases in how we gather our sample from our population, and so we have to consider that carefully and reckon with what that means. The methods we use in this class almost all assume that we have a simple random sample. So just remember that asterisk, that caveat, that limitation. If you've got a simple random sample, these methods will probably work very well.